Swayam Prabha. Digital India. Educated India.
Welcome back, my dear friends. A very good morning, good afternoon, good evening to all of you, and this is the TQM2 lecture series under the NPTEL MOOC, and this is the 35th lecture, and I am Raghunandan Sengupta from the IME department, IIT Kanpur. So, if you remember, we are discussing about the factorial models and their concepts and how the folds could be done, how you can divide into blocks. Blocks would basically consider the combination of the variables and their effects, and how the total combinations could also be considered. And obviously, the end of the day main emphasis was have the variables denoted in the leftmost column, then you will have the total sum of the squares of the errors for each variable, then you will have basically the degrees of freedom, and then you have the F test based on that you have the last column the level of significance. This is basically the overall viewpoint of ANOVA model. So, each time you will basically test an hypothesis H naught, say for example being such that beta 1 is equal to beta 2, or H alternative being beta 1 not equal to beta 2, or it can be, say for example, the standard deviations are same, sigma 1 square is equal to sigma 2 square, or the standard deviations being different, or the error being equal to 0, error being not equal to 0. Basically, you will have two alternative or opposing theories or concepts. You will try to test them using the analysis of variance models tables, and for that there are different methodologies based on which you try to find out the minimum number of factors, minimum number of variables, minimum number of attributes, which gives you the maximum amount of relationship. So, we will slowly see that how we have considered that. We have considered the factorial fractional model for of two variables or two levels. Levels means A and B being the variables, and A and B can be at two levels plus minus, then it could be 3 to the power k or 3 to the power k minus p depending on number of combinations you do, and it would be of the third order, fourth order, fifth order, the design setup which we have. So, these were the general discussion. We are trying to look at these type of problems from different angles. We will continue the discussions so on. So, we have basically the second level or the 2 level and one of the 3 level factors in the 2 to the power 3 design. So, if I considered, so you will basically have the runs would also be given, because before you prepare the ANOVA table the runs would be there. So, the runs are given on the leftmost column. Then you have the variables A, B, C. So, there are 3 variables, and consider they can be at 2 levels of importance. A can be plus minus, B can be plus minus, C can be plus minus. So, the total combination would be 2 into 2 into 2, that is 2 to the power 3 what we are considering. So, if you see the topmost part of this table, it is 2 to the power 3. So, these 3 concepts will be coming up, and obviously it can be 3 to the power 3, 3 to the power 4, or 4 to the power 3, whatever, depending on the levels. So, if you I am not digressing, just mentioning that if you have basically 3 variables at 3 levels, so it will be 3 to the power 3 such that A, B, C, A can be at 0, 1, 2 levels, B can be at 0, 1, 2 levels, C can be at 0, 1, 2 levels. Say for example, if I have A, B, C, D each being at 5 levels, so it would be 4 to the power 5. Now, continuing and the discussions, you have the combinations of A, B, A, C and B, C, and finally, a combination of all the factors taken together. So, if you consider the first row, so the effects of A, B, C are minus, and we are considering A, B, A, C and B, C at different levels of significance. So, hence the actual treatment combinations would be, if I try to find out, it would be A at low, high. I am just reading the second last column. A can be low, then high, low, high, and the corresponding values of x, which is the variable based on which we are trying to study, can be low, medium. So, obviously, what now we are trying to bring the concept of low, medium, high also into the picture by this different categorization. So, the average variance at these two pairs of runs could be used as the mean square of the errors. So, obviously, if you remember, I did mention in some of the classes in details, in some of the classes though fleetingly, that our main aim was basically to minimize the variance. That the square of the variance, we take the square of the difference of the actual value and the predicted value, which is the error, or the actual value and the average value, which is again the average error, square them up, sum them up, and that is basically the sum of the square of the errors. Now, if I read a table 9.11 analysis of variance for design done. So, you have the source of variations for A or combinations of x, Ax, and so on and so forth, which is the sources, and I want to find out the sum of the squares. So, the sum of the squares are SS suffix A, that is from A, SS suffix x, which is basically from x, the combinations of A, B, C taken in different directions. Then you have A into x, which is, and the last one being the error being E. The degrees of freedoms is given by, I am reading it 1, 2, 2, 4, and obviously the sum of all the degrees of freedom should be 7. And similarly, if I check at the lastmost row in this ANOVA table, you have SS suffix t, which is the sum of the squares of the total errors, which would be the sum due to all the variables plus the error terms. And then if I divide the corresponding values of the second column with the corresponding value of the third column, which is the sum of the squares and the particular value divided by its degrees of freedom in the second last column. So, now you have the mean square errors. Mean square errors would actually give you the values of f statistic. Based on that, you can comment the level of significance. If you are willing to assume that the two factor and higher interactions are negligible, we can convert the design in 9.10 into a resolution of 3 fractions with up to 4 levels factors and a single 3 level factor. This would be accomplished by associating the 2 level factors with 2 columns, which are basically A, AB, AC, and ABC. The column BC cannot be used for a 2 level factor because it contains the quadratic effect of the 3 level factors, which is coming out from X. This same procedure can be applied to the 16 combination, 32 combination, and 64 combination runs for the 2 to the power k design. So, obviously, there are k number of variables, each at 2 levels. So, hence we have the k to the power 2 to the power k design concepts. For the 16 runs, it is possible to construct a resolution of 5 fractional factorials with 2 levels of factors. Similarly, a 16 run resolution of 5th fraction can be obtained with 3 of the 2 level factors and 1 at the 3 level factor combinations. So, if we combine 4 2 level factors and a single 3 level factors in 16 runs, the design could be of the resolution 3, and we can change the resolution of 3 to 4, 4 to 3, and correspondingly such that the overall implication or overall information coming out from the study would be maximum. Now, we consider factors at 2 and 4 levels. It is very easy to accommodate a 4 level factor in a 2 to the power k design. The procedure for doing this involves using 2 level factors to present the 4 level factor model. So, what you are trying to do is that when you are trying to basically change from a 2 to a 4 or 4 to a 2 or 2 to 3, 3 to 5 or come down, it is like this, your overall concept. You are trying to basically divide your total errors. So, errors would basically consist of 2 parts. One is from the error, white noise, which you cannot predict, and another would be from the variability or from the variables or attributes, whatever it is. Now, my main concern is to basically find out the errors to the minimum extent possible using the minimum number of variables. So, if I am able to use only 2 factors or 2 variables or 2 attributes and basically give the experimenter the maximum amount of information, nothing like that. But it also may be possible that in each of the combinations of the variables, we would like to basically divide into subclass, as that the category of subdivision basically gives us the maximum set of informations. So, in that case, we will try to basically convert from a 2 factor to a 3 factor, 3 factor to a 4 factor, or the reverse way, such that our study gives us the maximum amount of information, giving us the maximum efficiency. So, if you remember if at all that we want to find out the efficiency, and in regression we basically have the R square, which is the sum of the squares based on which you are proceeding. So, we will try to basically predict the R square, which is 72% or 80% or 90%, whatever it is, it gives us to what level that we are able to predict. It can be either 72% or 80% or 0.8 or 90% 0.9, such that we are confident that our answer, depending on the number of variables we have considered and what are the variables, we are able to predict either 72% or 80% or 90% of the times in a prediction. That is to what is the level of accuracy. So, it is very easy to accommodate a 4 level factor in a 2 to the power k design. The procedure for doing this involves using a two level factors. So, there are groups of that and combine them and try to find out the 4 level factor design. For example, suppose that A is a 4 level factor, and you have basically levels given by the values of A1, small a1 suffix 1, small a2 suffix 2, small a3 suffix 3, small a suffix 4. So, it is a1, a2, a3, a4 with all the numbers 1, 2, 3, 4 coming in the suffix. So, we consider two columns of the usual table of plus and minus signs, say they are columns P and Q. The patterns of signs in these two columns is shown to the left of the table 9.12. The right side of this table shows how these 4 sign patterns would corresponding to the 4 level of the factors A. The effects represented by column P and Q and PQ interactions are mutually orthogonal. So, what you are trying to do is that trying to basically break them into orthogonal directions, as that whatever effect is coming from A should only be assigned to A. If B is orthogonal to A, then whatever effect we are assigning to B should remain there only. So, if we are able to break them into factors are orthogonal, such that our prediction would be of the utmost importance, considering that we can assign the level of significance on A or B or C or D, whatever they are, depending on the fact that they are orthogonal to each other. The effects represented by columns PQ and PQ interactions are mutually orthogonal and corresponding to the 3 degrees of freedom of the A effect. This method of constructing a 4 level factor from 2 level factors is called the method replacement. So, you are trying to basically replace from 4 of 1 to 2 of 2 type. So, that means you are trying to break them into more subcategories in order to do a better analysis of the prediction or analysis of the overall assignment of the errors. To illustrate this idea more completely, suppose that we have a 1 4 level factor and 2 2 level factors, and that we need to estimate all the main effects and interaction involving these 2 factors. So, this can be done with 16 run design. So, consider that table 9.13 shows the usual table of plus and minus signs for the 16 run 2 to the power 4 design, with columns A and B used to form the 4 level combinations which we have. Sum of the squares would be calculated for each of the column like A, B, so on and so forth till A, B, C, D, just as usual in a 2 to the power k system. Then the sum of the squares of all the factors which we have would basically be formed accordingly. Like if we have sum of squares of x, so x would basically be for A, B and A, B combined. So, you will have 3 levels, 3 no, I will not use the word level, 3 different variables. If it is C, we are only assigning to C, if it is D, we are only assigning to D, and if it is XC, obviously it would be AC, BC and ABC. Similarly, for XD it will be AD, BD and ABD. Similarly, for XCD it will be corresponding to that. Based on that, you find out the errors, you have the degrees of freedom, find out the root means, average root mean square, mean square values, find out the F statistic, pass your judgment depending on the level of significance. So, single factor, 4 level factor and 2 level factors in 16 runs are given. So, you have basically the runs are given the leftmost column, and corresponding to that you have A, B as the variables, then you find out x, then you have basically consider in the next level as C, D, and then combine them in such a way that the last effect which is there is coming from the combination of A, B, C, D, and you pass a judgment accordingly. So, thus this could be a 4 into 2 2 design. So, basically you have a 2 2 design and basically have such 4 different combinations or replications of them. So, if you are willing to ignore 2 factor interactions, up to 9 additional 2 level factors can be associated with the 2 factor interaction. or 3 factor interaction or the 4 factor interaction, and they can be found out accordingly. There are wide range of fractional factorial designs with a mix of 2 and 4 levels factors available. However, we recommend using the design cautiously. See, if all the factors are quantitative, that is, and the system is 2 to the power k minus p depending on the levels of importance you want to assign, or 2 to the power k minus p system with center points, it will usually be a superior alternative. Design with factors at 2 and 4 levels that are of resolution of 4th or higher order, which would usually be necessary if there are both quantitative as well as qualitative factors. So, we will define them and design them depending on whether they are quantitative or qualitative. Factors present and typically rather large, requiring about n greater than 32, such many cases which you have. So, now we will go into the realm of trying to find out the fitting the best regression model. So, in general, suppose there are single dependent variables or responses, so y. I mentioned about that, but I still repeat it, and there are k independent variables, which is x1, x2, x3 till xk. So, independent factor means that if you bring into the picture the concept of a matrix. So, this matrix X, which is from x, which consists of the variables x1 to xk, and each variable being of n number of durations of time frames. So, obviously, it will be depending on your nomenclature, it would be n cross k or k cross 1 matrix. So, obviously, we should remember that the rank of the matrix is k, which basically is the number of independent such variables which you have. Point 1, point number 2, in general multiple linear regression, we consider all the x's are normally distributed. We also consider they are orthogonal or they are independent of each other. If they are not independent of each other, the rank would not be k, it would be less than k, which is not possible. We will also consider the errors are independent of each other. We will also consider the covariance existing between the errors and excess values are 0. The point which I just mentioned before that the errors are independent of each other, which would also mean the covariance existing between the errors is also 0. We will consider the errors have a fixed variance. We will also consider the errors have a mean value of 0, and obviously we will have the expected value of x1 to xk would be different values, which will be mu 1. So, that is suffix 1, mu suffix 2, mu suffix 3 till mu suffix k. Similarly, the variances of x1 to xk would be again independent of each other. They would be sigma suffix 1 square, sigma suffix 2 square, sigma suffix 3 square, so on and so forth till the last value is sigma suffix k whole square. And then obviously, y is a dependent, y which is dependent variable is dependent on this x1 to xk being multiplied by the respective values of beta 1 to beta k, which are the coefficients, and obviously there would be error term which is epsilon. So, this beta 1 to beta k are the values which actually means what is the partial derivative, the rate of change of y with respect to x1, what beta 2 would basically mean what is the rate of change of y with respect to x2, and so on and so forth. So, this I had repeated, so hence I am again repeating it without showing or going through the small assumptions as statements. So, in general, suppose there is a single dependent variable response y that depends on k independent or regressor variables. For example, there are x1 to xk. The relationship between these variables is characterized by a mathematical model called the multiple linear regression or regression model. The regression model is fit to a set of sample data points which are n in number. In some instance, the experimenter knows that the exact form of the true functional relationship between y, x1, x2 till xk is given, and say that is given by y is equal to some function of x1 to xk. However, in most cases the true functional relationship is unknown, and the experimenter chooses an appropriate function to approximate the functional value phi. So, low order polynomial models are usually utilized to find out the best fit. So, now we are slowly expanding our discussion away from the realm of multiple linear regression. So, now if we come to the linear regression model, suppose that we wish to develop an empirical model relating the viscosity of a polymer to the temperature and the catalyst feed rate which is being given. Consider the model is given like this: y is equal to beta naught. Beta naught is basically the intercept. So, if you remember in class 10 or 11, we consider y is equal to mx plus c. So, this c is basically the value of beta naught which we have. This is the intercept at where it is cutting the x axis. Now, here again, if it is y is equal to beta naught plus beta 1 into x 1 plus an error without any x 2 terms, it means that we are able to draw in a Cartesian coordinate of 2 dimensions. So, along my left arm the y axis, along my right arm you have basically the x axis. So, I plot the values on this Cartesian coordinate, and the value where the line best fit line cuts the y axis, basically the value of c or beta naught here, and this beta 1 would basically be the rate of change of that function or the tan of this best fit line with respect to which is basically the divide of dx x 1. I should not be using the word x, and then it will give you the problem solution. So, if I have the best fit here, let me draw it. So, these are the points, this is the best fit line, these are the errors, this is the value of beta naught, this is the theta degrees, tan of theta is equal to beta 1, this is the y variables which are the x variables, y is dependent, x is independent. Okay. Now, the question is that why did I mention that? Consider that you go into 3 dimension one. Again, y you are measuring along my left arm, which is basically going vertical up towards the roof of this room where I am basically giving the lecture. The x 1 values are basically on my right arm, going from this point on to my right, and consider nomenclaturally x 2 is there, which is basically from the same point and is going towards you. So, that basically these x 1 and x 2 is the floor in the room, and the y is basically going to the roof. Now, if I plot y is equal to beta naught plus beta 1 x 1 plus beta 2 x 2 without the error, either I am not considering, and if it is a linear line, then it will basically be planes in this room. Now, if I am looking at the plane from the direction of x 2, or am I looking at the plane in the direction x 1, it will mean that one of them is fixed. So, if I basically project it onto the wall, any wall which I have, then we will have basically respectively the equation corresponding to y is equal to depending on x 1 or y depending on x 2, considering that we are basically trying to fix either x 2 or x 1 depending on which direction we are looking at. So, now if I have the equation as y is equal to beta naught plus beta 1 x 1 plus beta 2 x 2 plus epsilon, where y represents the viscosity, x 1 represents the temperature and x 2 represents the catalyst feed, these are the 2 variables. Then a multiple linear regression with 2 independent variables is fitted. We often call the independent variables or predictor variables or regressors. The term linear is used because the equation which you have written is a linear function of the unknown parameters beta naught, beta 1, beta 2. The model describes a plane in a 2 dimension, as I just mentioned. In the x 1 x 2 space, the parameter beta naught defines the intercept of the plane onto the y axis. We sometimes call beta 1 and beta 2 as the partial regression coefficient, because beta 1 means the expected change or the rate of change of y per unit change in x 1, while x 2 is basically being held constant, while beta 2 measures the expected change in y per unit time with respect to x 2 given x 1 is constant. Exactly what I mentioned in the pictorial way, it is being mentioned here in the slides. In general, the equation can be expanded. Now, we have a multiple linear regression with k independent variables, y is equal to beta 1 plus beta 1 x 1 plus beta 2 x 2 plus dot dot till beta k x k plus epsilon, which is the error. This is the multiple linear regression model with k regressor variables. The parameters beta j, where j is equal to 0, 1, 2, 3, 4 till k are called the regression coefficients. Beta naught is the value at which there is no independent variable and it basically cuts the y axis or touches the y axis or the planes which is there, the hyperplanes in the n dimensional where it touches the y axis. This model describes a hyperplane. In the k dimensional space of the regressor variables xj, the parameter beta j represents the expected change in response of y per unit change in xj when all the remaining variables are considered to be independent or they do not change. So, it means that beta 1 is the rate of change of y with respect to x 1 keeping x 2 to x k as constant. If I consider beta j, it means basically the rate of change of y with respect to x j and keeping x 1 to x j minus 1 and x j plus 2 till x k as constant. So, that means the variables corresponding to the rate of change would only be considered that that variable is changing, others are being kept fixed. More models are more complex, can be built up, and in appearance, say for example, we can consider the model as y is equal to beta naught plus beta 1 x 1 plus beta 2 x 2 plus beta 1 k x 1 into x 2 plus can be another term can be beta 2 1 x 2 into x 1, but we will consider beta 1 2 and beta 2 1 as to be equal, because when we try to differentiate the function of delta f with respect to x 1 and then again differentiate that differentiation with respect to x 2, it will give me the same value if we differentiate it first with x 2 and then with respect to x 1, which means del 2 f del x 1 del x 2 is exactly equal to del 2 f del x 2 and x 1. That means the differentiations are symmetric. So, and the model can be y is equal to beta naught plus beta 1 x 1 plus beta 2 x 2 plus beta 1 k x 1 x 2 epsilon. If we basically put x 3 as equal to x 1 x 2 and beta 3 as x 1 x 2, then the equation can be written as y is equal to beta naught plus beta 1 x 1 plus beta 2 x 2 plus beta 3 x 3 plus epsilon. So, which is a standard multiple linear regression model with 3 regressors x 1, x 2 and x 3. Now, we want to basically estimate the parameters of linear regression model. So, the method of least square is typically used. What is the method of least square? Basically, we try to find out the errors, square them up, sum them up and try to basically minimize that error with respect to something. What we are going to do that? We are going to come that within few minutes. So, the method of least square is typically used to estimate the regression coefficients in a multiple linear regression model. Suppose that n is greater than k, k is the number of variables and n is basically number of readings. So, n is greater than k observations on the response variables are available, say they are w1, y1, y2, y3 till yn, and similarly the values of x1 to xk are given from the corresponding first value to the nth value. So, if I consider x1, it will be x11, x12, x13, x14 till x1k, where the first suffix basically denotes the variable and the second suffix 1, 2, 3, 4 till n, or not k, till k n would basically mean the reading number. Similarly, if I have x21, x22, x23 till till x2n, it will basically mean the second variable values are from first to the nth one. Similarly, the last variable set vector would be xk1, xk2 till xkn. So, the xk1 is basically the first value of the kth variable, xk2 is the second value of the kth variable, similarly xkn is the nth value of the kth variable. Along with each observed response yi, we have an observations on each regression variables, and let xij denote the ith observation at or a level of variable xj. The data would basically given as given in table 10.1. We assume that the error terms epsilon in the model is such that the expected value is 0. If you remember that, I had mentioned that few minutes back in the last to last slide. And the variance, if you also remember, I mentioned that is fixed, and also I mentioned that the covariance existing between two errors is 0, and obviously the error value is fixed, which is given here as sigma square. And that the epsilons are uncorrelated random variables, they are uncorrelated or not related to each other. We may write the model as given, that means yi is equal to beta naught plus beta 1 x 1 I1 plus beta 2 x I2 plus plus beta k x I k plus epsilon. So, you basically put it in the form as this. Now, what is important is this, I will explain that later. We basically find out the squares of the errors, that is y1 minus y1 hat, y2 minus y2 hat, square them up, add them up. So, when you are adding them up and basically try to minimize it, you will find out there are variables which are unknown. So, what are they, you will ask? So, they are basically beta naught, beta 1, beta 2 till beta k. You will basically partially differentiate them with respect to beta naught, beta 1, beta 2 till beta k, have such k equations, equate them to 0 and find out beta hat, beta 1 hat, beta 2 hat till beta k hat. So, once you find out these estimates, you will again use them for the nth plus 1 reading and do the calculations accordingly. So, with this I will end the 34th lecture, continuing more discussions of the regression model in the 36th and the corresponding lecture. Thank you and have a nice day.